Hello and good evening, everyone. Well, it's practically good night at my place. Anyways, today I'm going to present to you a paper, Sparsity in Covering Solution, authored by Pallavi Jain and me, Manveer Singh Rathore. Two of the well-studied covering problems are vertex cover and feedback vertex set, and these are the problem focused on majorly in this paper. So first of all, let us see what vertex cover is. So in very simple words, delete vertices such that no edge remains in the resulting graph. Or we can say pick a set of vertices such that no two unpicked vertices have an edge. In this graph, as you can see, if I pick 4 and 5 in the solution, then no unpicked vertex have an edge between them. Or if I pick 4 and 6, then also there are no edge between any of the unpicked vertices. Now let's come to sparse vertex cover. In this, there are two major highlighted portions as you can see. So the definition is pick a set of vertices of size less than equal to k such that no two unpicked vertices have an edge and edge between picked vertices are less than equal to t. So here as you can see I have highlighted size less than equal to k and edges between picked vertices less than equal to t. So for example, if I say like I pick 4 and 5 as my vertex cover, then there is an edge between 4 and 5. So if t is equal to 0, then this is not a practical solution for sparse vertex cover, but if t is equal to 1, then this is fine. And if I pick 4 and 6, then there are no edges in the vertex cover. So if for t is equal to 0 also, this vertex cover works. Now let's come to feedback vertex set. By in simple definition is delete vertices such that no cycle remains. Or in other words, pick a set of vertices such that every cycle passes through at least one of those vertices. For example, in this graph, if I pick 5, then all the cycle in this graph definitely passes through 5. And if I delete 5, there are no cycle in this cycle. There will remain no cycle in this graph. If I pick 4 and 7 and delete them, then also there will be no cycle in this graph. So now let's look into sparse feedback vertex set. In sparse feedback vertex set, we pick a set of vertices of size less than equal to k such that every cycle passes through at least one of those vertices and edges between picked vertices are less than equal to t. So here also the same two highlighted parts that they exist. Edges between picked vertices should be less than equal to t and the size of the set should be less than equal to k. In this example, if I pick 5, then this is the vertex of feedback vertex set and the edges in the set is 0 since there is only one element. Now let's come to the classical complexity of this problem. For vertex cover, it is NP hard and feedback vertex set is also NP hard. But there are two versions of this problem, independent vertex cover and independent feedback vertex set. Independent vertex cover is polynomial time solvable. Independent feedback vertex set is NP hard. Our problems are the generalized version of independent version of this vertex cover and feedback vertex set. If in our problem we put t is equal to 0, then our problems become the independent vertex cover and independent feedback vertex set. Now, first let's look at what is parameterized complexity. In parameterized complexity, each instance is associated with an integer k, which is known to be the parameter. Our goal is to design an algorithm with running time that is function of k and a polynomial in n. When before going to the algorithm, we do a kernelization process. In kernelization is a data pre-processing it's a pre-processing technique to efficiently trim the data. What I mean is, for a given instance of a problem I comma k, we reduce it to another instance of the same problem where I dash comma k dash, where I dash is upper bounded by a function of k. Now for results, existing results for vertex cover is 2k is the linear kernel, but in R we have in sparse vertex cover we have a quadratic kernel. In vertex cover there is an algorithm known in 1.25 284 to the power k. And this sparse vertex cover we have designed an algorithm of time complexity 1.3953 to the power k. And so on in the feedback vertex set, there is a quadratic kernel 2k square plus k, and in our case we have a power 4 kernel, and also the algorithm for feedback vertex set is 3.46 to the power k, and in our case we have 5 to the power k algorithm. Now let's come to sparse vertex cover. We design a new problem called constraint sparse vertex cover, which is equivalent to our problem. So what is constraint sparse vertex cover? In constraint sparse vertex cover, in input there is given a graph G, a set X, and a non-negative integer K. The question is find a set S as 0 to Sk such that for each I belongs to 0 to K, if G minus X does not have a vertex cover of size exactly I, then Si should be is equal to Z, where Z is just for technicality. And if there X or otherwise, Si is a vertex cover of G minus X of size I that maximizes sparsity, which also means that minimizes the number of edges in the solution. So what we will do is we will go case by case for all component, how it looks or how a specific property that it holds, and we will do the branching, or if if it is polynomial time solvable, then we will see why. So here the first one highlighted part, you can see it is a path. So we have designed a dynamic programming approach for to solve the CSVC for a single path. In the right side, you can see the graphs. This graph holds a specific property that there are at most one vertex with degree more than 2. So in that case, what we do is we just branch on the vertex of, I mean by branching, I mean guess whether that vertex will be in the solution or will not be in the solution. We just guess for the highest degree vertex. In this case, we will check if whether we will go in solution, or in this right one, we will check if there you will go in the solution or not. And in both the cases, the remaining graph, after deleting that vertex or its neighborhood, the remaining graph will become a group of paths, and that we can solve using our dynamic programming approach. Uh, so then let's come to components uh, having vertex with degree at least 4. So in this case, what we do is we just simply branch on the vertex with degree at 4 or more. So that gives us a branching vector of 1, 4. Either we take that vertex in the solution or its neighborhood. After that, constraint sparse vertex cover. In this, if the component have at least 1 degree 1 vertex. So the first case, A part is already handled and that can be solved in polynomial type. In the B case, what we do is we branch on X. We either take X in solution or neighborhood of X in the solution. In the case when we take X in the solution, then V and U, let me just a second, then V and U become a path that will give us at least one size vertex cover in polynomial time. So we can effectively say that its branching vector is 2, 3. In the next case, if we branch on X, then it's 1, 3 branching. But in the case when X is in the solution, the remaining graph containing V, U, and Y, this becomes the same as case B, which gave us 2, 3 branching. So efficiently, this branching will become 3, 4, 3 branching. And similarly, we can solve all the remaining cases also. Like in the D, if I branch on Z, then the remaining graph will become polynomial solvable, containing V, U, Y, and X. And after that, 1, 3 branching will be converted into at least 2, 3. And then similarly for all the remaining cases also, if the graph contains a degree 1 vertex, then we can solve it. And these are all the possible cases of a component containing a degree 1 vertex that is proven in the paper, and these cases are exhaustive. After that, we know that our graph does not contain a vertex with degree more than 3 and also does not contain any vertex with degree 1. So now if a component have a triangle, then in the first case, this is a polynomial time solvable problem. As I said, if the graph is small, as I forgot to mention that if the graph is a small size graph or a constant size graph, then we can simply guess on each and every vertex, and whether it vertex will be in the solution or not will be in the solution. But since it's a small graph, so guessing for each and every vertex will not cost us much time and will be polynomial time only. For the second case, if I branch on W, the only degree 3 vertex, then the remaining V comma U will become a path when I take W in the solution, and this U comma V H will give us at least one size vertex cover. So the efficient branching vector will be 2 comma 3. In the next case, if I branch on any of the degree 3 vertex V or W, then also when I take suppose W in the solution, then the remaining U, V, and the remaining graph will become case previously handled in when u will become degree 1. So in that case, we had a branching vector of 2 comma 3. So efficiently, our overall branching vector will become 2 plus 1 comma 3 plus 1 comma 3. It will be 3 comma 4 comma 3. And then in the last case, we branch on W, where W have the least neighbor in X. X is the set that is given in our input, where W has the least neighbor in X when neighborhood. And what we do is when we take neighborhood of W in the solution, then we know that neighborhood of U and neighborhood of V will always be in the solution. So I will not go in the technicality, but just giving you a reference. Since we are we have a limit on time. So as you said, when neighborhood of W is in the neighborhood of W is in the solution, then we know that neighborhood of U and neighborhood of V will also be in the solution. Then comes the case. So the overall branching vector for this case will become 3 comma 4 comma 3. Now comes the case component have degree 2 vertex. Then what we do is we simply branch on this. In first case, what we do is we simply branch on W, and after that the remaining graph will become, as I said, U will become degree 1 and V is degree 2. So there, for that case, we know that we have a 2 comma 3 branching. So overall branching will become 3 comma 4 comma 3. In the second case, we have a special condition, then only we will apply this branching. If neighborhood of U are less than equal to neighborhood of U in X is less than equal to neighborhood of V in X minus 1, then what we do is we either take neighborhood of W in the solution, or we take U and W both in the solution. So I will not go in detail due to the lack of time. And so overall branching vector will become 3 comma 4 comma 3. And after that, if component have all degree 3 and degree 2 neighbors, so for the A case, we know that since this is a small size constant size component, so we can solve it in polynomial time. For the B case, we branch on X and U. Since so in the left image, if you can see, if we branch on X and U, then the graph containing S, V, A, and V, S, V, A, and V, this graph becomes a small graph which have at least one size vertex cover, and that can be found in polynomial time. So overall branching vector will be 3 comma 4 comma 3. Now in the C case, what we can do is we can simply branch on X and W, and when X and W are in the solution, then the remaining graph will give us at least two size vertex cover. So the effective branching vector will be 3 comma 4 comma 4. And similarly, we can solve for all the cases, and the branching vector, overall branching vector will be 3 comma 4 comma 3. Now for rest all components, let us see that in the first case, what we do is we simply branch on Z and P, and when Z and P both are in the solution, then the graph containing X, V, and Y will give us a one size at least a one size vertex cover. So the overall branching complexity will be 3 comma 4 comma 3. In the second case, what we do is we branch on neighborhood of V, neighborhood of Z, and if first branch will be neighborhood of V, which is 3 size 3, neighborhood of Z, which is size 3, and if they are not in the solution, then we take V and Z and P and Q in the solution. Since if we don't take P, then we have to take Y, and if we take Y, then we can simply replace X and V in the we can simply replace X and V due to the previous result that we said, if there is a degree 2 near degree 3, then it has to follow a specific condition, or else we would have already branched on it. So this will give us 3 comma 4 comma 3 branching. And similarly for this graph also we will have a 3 comma 4 comma 3 branching. So overall branching vector will be 3 comma 4 comma 3. And so the all in all the cases we got a 1 comma 4 branching and 3 comma 4 comma 3 branching. So the worst one from both of them is 3 comma 4 comma 3, which gives us a time complexity of 1.3953 to the power k. Now let's coming to sparse feedback vertex set. First we bound the high. So the ideology behind this kernel is bound the high and low degree of graph, then bound the number of vertices in the graph using the bound on the degree. So first of all, we find all the k plus 1 flowers and mark them m. So what is a flower? So in this graph, as you can see, U is a 4 flower because U has four disjoint cycles passing through it. So what a flower means is k plus 1 flower means is a vertex having k plus 1 disjoint cycles passing through it. those cycle are not exactly disjoint, but they intersect at exactly one point, that is U. So what we do is we add a self loop on U and we mark U as M. And now in second step, what we do is delete vertex having degree 1 in G minus M, since M will always be in the solution because we added a self loop. And now in G minus M, the degree 1 vertex will not take part in any cycle, so we can just delete it. If there are two unmarked degree 2 vertex as neighbors, then we delete one. So here, as you can see, V and U are degree 2 in G minus M, and U has more neighbors in marked vertices and V has less neighbor in marked vertices. So it is better to keep V than U, since if we take all the cycle passing through U are also passing through V and all the cycle passing through V also passes through U. So in the solution it will be better to have less edges. So we will take V in the solution. So for that what we will do is we add a edge between V and U's other neighbor and delete the edges between U and its neighbor. So from the literature, we know that for a graph H, a vertex V belongs to H with a self loop. If there is in polynomial time, we can find either if there exists a k plus 1 flower at V, or what we can do is we can find a 2k sized set which intersect every cycle that passes through V. So for each vertex in G minus M, we find ZV, and so the graph now looks like something like this. So this five elliptical bodies that you can see, they are the component directly connected with V and they don't pass through Z. And the orange graph is the graph that is maybe connected through V, but all the connections goes through ZV. So if the elliptical part has a cycle in between them, inside that, so we mark that, mark K. If there are more than K such components, then we can simply say that this is no instance, or else we mark K. There can be cycle between V and Z, so we also mark Z and V. And now there can be if there exists a vertex in Z that has two neighbor in any component. So what we do is for each vert uh, sorry each vertex in Z, mark K plus 2 such components which have two neighbors of a single vertex. So for each word of that vertex, so we mark K plus 2 such components. After that, what we do is if for every vertex in ZV, we mark K plus 2 components that have an edge with that. After that, we for every pair of vertex in ZV, we mark K plus 2 common neighbors. So for an X and Y vertex in ZV, if both of them share an edge with a component, then we mark K plus 2 such components. Now, since we know that how many components have we marked, and we know that that has a bound, since we always counted how many we are marking, what we will do is we will delete the edges between V and all the unmarked components. So we will just delete this yellow edge. And now what will happen is degree of so now V's degree is bounded. So if we repeat this process for each vertex in the graph G minus M, then degree of each vertex in G minus M, G dash equal to G minus M, is bounded by order of K cube. And from the literature, we know that let H be a graph with minimum degree at least 3, maximum degree at most delta, then a feedback vertex set of size at most K only exists. Size at most K exists. If then the H has at most delta plus 1 into K vertices and 2 delta K edges. So by this we know that number of vertices in G is equal to number of vertices in M plus number of vertices in G dash, which is equal to order of K4. So due to time constraint, we are only going to discuss these two things, the algorithm for SVC and the kernel for SFVS. So for the future scope, we have the problem itself can be expanded into density in covering solution also. And another thing that we can do is a parameterized approach can be thought of with parameter T also. So if there are any questions, since it is recording, so there won't be any question. So thank you.